Hello students, last video we were discussing about the basics of pipelining, how it is being implemented and the different stages of this pipelining and the various operations that are part of insertions to be given into a pipeline system and how it can be demonstrated, and we have seen some examples also. Now in this session we will see some of the performance issues with the concept of pipelining. As the pipelining increases the CPU insertion throughput, that we already know as per our previous session and given examples. We have already understood that it will automatically increase the speed of the CPU and it will improve the performance, but it will not reduces the execution time of an individual instruction. So pipelining it will actually increase the throughput, means more results can be produced by or within a given limited time. But as we see separately, for each insertion will be taking its own time. If it is 5 clock cycle, the insertion will be taking 5 clock cycle itself. But on an entire system, when we consider a number of insertions, we can see that the throughput or the time taken for the entire task will be only less. So it usually increases the execution time of each insertion due to the overhead only. So see the problem related to the pipelining. It increases the execution time. So what we were saying earlier, it will have only less time for the execution of an individual insertion. But when it comes to the real pipeline, there will be some additional time will also be taken due to the overhead in the control of the pipeline. So due to some problems that are part of the pipeline, there will be some overhead that may happen, something extra to be done, or there will be some delay in time, so that automatically the execution time will also be affected for each of the insertion present in the or that is submitted to the computer system. So the limit arises from the imbalance among the pipe stages. So as per our previous example, every stages were balanced. That means first insertion, first operation, then first insertion, second operation, automatically second insertion arrives. But everything is balanced, everything is following that single clock cycle and it will complete its execution. But there can be some problems in between. So if any simple problems occur in between these pipe stages, automatically it will affect the entire system by reducing the performance or the speed of the entire computer system. So it is usually called as it is because of the overhead happens with the pipelining architecture. Now the pipeline overhead arises from the combination of pipeline register delay and the clock skew. It is because of the pipeline register delay. So there was a pipeline register that was placed in between different stages. So if some operation is given the result to the pipeline register and it could not hand over that input to the next stage, there will be some delay. Automatically one stage will be cancelled on that particular clock cycle. That clock cycle will be wasted. Automatically, if some problem happens at one particular clock cycles, it may affect the all the remaining stages of the remaining insertions also. So sometimes there will be a clash between two insertions by having the access to the same ALU at the same time, or maybe some access to the register file by more than two operations or insertions at the same time. It may happen if the balance is being varied. So if everything is balanced properly, it is okay, but it is not always possible. So there is a sure chance of having the imbalance between different stages, and one is because of the pipeline register delay. If the register is not forwarding the result to the next stages in time, there will be a delay. Maybe because of if some pipeline register is under failure, that time also this delay happens, or due to some other reason there may be some delay between two different stages. And also there is a problem called as clock skew. Clock skew is because of some variation in time. Skew is actually a time variation, because if a task is to be completed within that cycle, if it is not completing and it is taking more time, so sometimes it may take more time, so there will be a clock skew, there will be some time variation, it will affect the remaining stages also. So due to the pipeline register delay and clock skew, there will be having a lot of overhead arises to the pipeline, and due to this overhead the entire performance of the computer system will also be affected, so that it will reduce the parallelism by taking more time, so that it will be slightly affecting the throughput of the entire system. Now we will see one example based on the previous session. Consider the unpipelined processor in the previous session that we were discussing as the first processor that is not being pipelined. We are having separate set of instructions to be executed one after another. Assume that it has a 1 nanosecond clock cycle, so it is taking the parameter as 1 nanosecond. One clock cycle can be of any dimension, so normally it is 1 nanosecond, and that it uses 4 cycles for ALU operation. So it is not like the example given in the previous session, because not all the operations take only one clock cycle. So sometimes depends on the operation, the number of clock cycles required for a particular operation will also be varying. So that depends on the operation itself. That is what I was mentioning. All the operations will not be done, or that won't be happening in balanced mode. So if that balance is being varied, it may affect the entire result. So 4 clock cycles for ALU operation and branches. So for both ALU operation and branches, it uses 4 clock cycles, and 5 clock cycles are utilized for memory operation. So there are 3 operations: ALU operation, branch operation, memory operation. 4 clock cycle for ALU operation, 4 clock cycle for branch operation, and 5 clock cycle for memory operation. Now assume that the relative frequencies of these operations are, so 40% of operations are ALU operations, 20% of operations are branch operations, and 40% of operations are memory operations. So we are considering one entire system where 40% of the operations are from ALU, 20% from branches, and 40% from memory operations. Suppose that due to the clock skew, because of some clock variation, time variation, and setup, and due to some setup, pipelining the processor adds. So pipelining will add 0.2 nanosecond of overhead to the clock. So that is the imbalance. If some problem happens due to the clock skew that I was mentioning before, and due to some other setup between, or it is due to some register delay and all, an overall overhead of 0.2 nanosecond is given as an overhead to the clock. So the processor adds. So if it is following pipelining, an overall lagging of 0.2 nanosecond will also happens to the clock. So because of some problems related to pipelining. Ignoring any latency impact, how much speed up in the instruction execution rate will we gain from a pipeline. So even if we are having some problems, so that is the major advantage of pipelining. We are having some imbalance problem, we are having some delay problem, we are having some clock skew problem, whatever it be, we are actually implementing pipelining. We are getting some lagging in clock cycle times and all. Still we can have some advantage, not some advantage, only few advantage will be lost, and we will be getting more advantage if we are following a pipeline architecture. So just for giving an for getting that idea, we are using this example. So some of the operations are executing in pipeline mode, and there are some pipeline delay or some overhead also happens, and it will lose some more time due to that overhead. And even after having this overhead, then also we are actually gaining some parallelism. That is the indication of this problem. This is not actually a problem, just having a look at a situation where we are getting some gain on this pipelining mechanism. So the average instruction execution time on the unpipelined processor is the instruction execution time we discussed earlier in our previous chapter. So it will be like clock cycle into average CPI. So CPI is cycles per instruction. So total cycles means if you are having some 100 instructions available, and we are taking the average cycles per instruction. So each instruction takes this much number of cycles, and we are taking the average of that into clock cycle time, that is the 1 nanosecond that is given here, and it is 1 nanosecond into, we are taking the average CPI. So 40 plus 20 into 4. So 4 clock cycles are given for 40% for ALU and 20% for branch. Okay, 40% for ALU and 20% for branch, and 4 clock cycles are utilized by ALU and branch. So 40 plus 20, that is total 60 into 4, 60% into 4 clock cycle, plus then remaining 40% is having 5 clock cycle, that is for memory operation, 40% into 5, which is equivalent to 1 nanosecond into after the calculation evaluating this, we are getting 4.4, which is equivalent to 4.4 nanosecond. 4.4 nanosecond is the time, the average instruction execution time in this particular situation when there is no pipelining being implemented. When there is no, so initially we are considering the situation when we are not implementing pipelining, and the instructions are executed one by one, and for the number of clock cycles for each operation, and totally it will take 4.4 nanosecond. Okay, so for executing one ALU operation, branch operation, and memory operation, totally it will take 4.4 nanoseconds. So one clock cycle is 1 nanosecond. So for this entire set of operation, it will take 4.4 nanosecond. Now in the pipeline implementation, the clock must run at the same speed, at the speed of the slowest stage plus overhead, which will be, so slowest stage is actually 1 nanosecond, and the overhead is actually 0.2, as we have mentioned here in the question. 0.2 nanosecond overhead is due to the overhead that happens with the pipeline. So this is the average instruction execution time. Thus the speed up from pipeline can be calculated or evaluated based on the following. So see, the same thing will be implemented here. So the 1 plus 0.2 is the average execution time, because 1 is the normal 1 nanosecond is the normal clock cycle speed, but 0.2 is already given as an overhead. So 1.2 nanosecond is the average cycle time that is taken now. Now the speed up can be evaluated by using this concept, that is speed up can be evaluated as, now we have already seen how we can calculate speed up. The speed up from pipelining can be taken by average insertion time unpipelined to the average insertion time pipelined. Okay, so for any speed up, you have seen in the previous module itself, average insertion time unpipelined took 4.4 nanoseconds, and if it is pipelined, average insertion, as we were mentioning before, average is 1, because we are having some initial delays, but still later if it goes into this pipeline stages, an entire set of operations of different insertions to form the set equivalent to the one entire insertion, that will be completed within 1 nanosecond. So that 1 nanosecond plus we are taking 0.2 an additional time for the delay and all. So 1.2 nanosecond is the insertion time for a pipelined machine. So which is equivalent to 4.4 divided by 1.2, that is 3.7 is the value that we are getting as the speed up. So speed up due to pipeline. So if there is no pipeline, it took 4.4 nanosecond. If it implements pipelining, it took 1, plus due to some skew and all 1.2, but we have gained a speed up of 3.7 times better than the unpipelined architecture. Okay, so just thing is, some task is given to the unpipelined system, it take 4.4 nanosecond average time, but if the same is given to a pipelined architecture, it will take only 1.2 nanoseconds. So automatically the speed up is 3.7. So this pipelined system is 3.7 times faster than unpipelined system. So the 0.2 nanosecond overhead essentially establishes a limit on the effectiveness of pipelining. If the overhead is not affected by changes in the clock cycle, Amdahl's law tells us that the overhead limits the speed up. Okay, so it will actually limit the speed up, but still we can see that we are having a huge speed up when compared to the normal unpipelined architecture. So whatever be the problems, the additional problems, additional faults of this pipelined architecture, we are having some some improvement or some increase in the speed, or we are having some savings in the total time for the completion of the entire task. So that is the advantage of using pipelining, even if we are having some problems in between the execution of this pipelining architecture. Now next is pipeline hazards, the different problems, some threats that may happen during the execution of the entire pipeline procedure. So there are some problems and that is to be handled. So this session we will see what are the hazards and how it can be evaluated, and the specific hazards will be discussed in the next video. So what do you mean by hazard? Hazard prevent the next insertion in the insertion stream from executing during its designated clock cycle. So one task is designated for a particular clock cycle, that is 2, but it is not happening, it is delayed due to some reason, that is being delayed. So it prevents the next insertion in the insertion stream from executing during its designated clock cycle. So due to the problem of one insertion, the next insertion cannot be executed at the designated clock cycle. That is called as hazard. That is a major problem of the pipeline system. So hazard reduces the performance, as you know. If some insertion is being delayed, automatically it reduces the performance from the ideal speed up gained by the pipelining. There are basically 3 classes of hazards. We will just see what are those hazards. We will see in detail on these hazards in the next video. So first one is structural hazard. So this delay happens because of resource conflicts. if some resources are not available, if some resources are being utilized by some other instruction, or if some instructions are not at all available. So in that situation, there will be a delay for the next instruction to be continued. Okay, so it will automatically affect the entire execution time of the pipeline system. So it arises from resource conflicts when the hardware cannot support all possible combinations of instructions simultaneously in overlapped execution. So due to some structural problem, if some memory, for example, some memory is not available, or if some register is not available, it cannot be given to some other instruction. If some conflict happens, there is a chance of this delay. It prevents the next instruction to be executed in the designated cycle. Okay, it will be executed later on some other cycle, but that is actually being delayed. Now you will see that later. Now second hazard is called as data hazard. It arises when an instruction depends on the result of a previous instruction. So sometimes if we execute these instructions in parallel, the problem is sometimes this instruction is expecting the result of this instruction, but the result of this instruction will be produced only on this clock cycle here. But the next instruction requires the same thing at this point of time. That time the result is not ready. So automatically this will be delayed. It is to be waited till the completion of the previous instruction, then only. So there will be a delay. So it is designated to execute on this clock cycle, but it will be delayed to this time. So automatically the entire execution will be delayed. Maybe the result of this will be, this may be required for some other instruction. So automatically the entire procedure will be delayed for some time. So it will affect the entire performance of the system. So the second type of hazard is called as data hazards, and third hazard is called as control hazards. It arises from pipelining of branches when we use branch instructions and when the instruction changes the PC program counter. Sometimes if the program counter value changes due to some operations, it cannot decide that what will be the next instruction to be executed. So this is the branch instruction, then next is designated, but due to branch will be executed here. Maybe it need to go to some other instruction, some other location. This is to be executed, but automatically the second instruction started execution and it is in the middle stage. So that cannot be permitted. So this is to be some solution to be done by blocking this instruction, because branching happens, it goes to some other location. We cannot have the execution of the next instruction at that particular moment. So some solution must be there. So hazard happens, it will delay the remaining instruction and it will affect the entire performance of the system. So three types of hazards: structural hazards due to resource conflict, data hazards due to the unavailability of the inputs from the previous stage, the delay happens, and third one is control hazards, similar to the second one, the wrong instructions being executed regardless of the branch exactly what is to be executed. Now the problem that happens with hazard is it will stall the pipeline. Stall means it is like a gap will be formed. It is also called as a bubble. A bubble will be formed so that time cannot be utilized properly. So if any hazard happens due to some structural hazard or data hazard or control hazard, there will be some stall. That means some empty area, that is nothing will be happening at that particular designated clock cycle. The clock cycle will be wasted and then their procedure will be delayed for some time. So that is actually called as, so that delay in the pipeline is actually called as a stall, formation of a stall. So avoiding a pipeline often requires that. So sometimes we need to avoid the pipeline itself due to the formation of stall. It requires that some instructions in the pipeline be allowed to proceed while others are delayed. So some insertion will be delayed and some other insertion to be proceed. So sometimes due to stall, some for some area we need to avoid the pipeline also. So we need to have some resolution on different situations based on the type of hazards present. So so it is actually considered as a major problem of pipeline. So due to these hazards many problems happen, so we should have some provision for the solution of that hazard also. So while finding out that solution, we need to have some additional thing to be added to the pipeline architecture. That will again increase the cost as well as it will affect the overall speed of the pipeline also. Still finally the conclusion is like the pipeline, whatever be the additional problems, whatever be the additional requirements, final advantage that we are getting with the pipelined architecture is higher when compared to the unpipelined architecture. So we'll see the performance of pipelines with stalls. So when we are having some stall being present in between the execution of pipeline stages, how we can evaluate the performance on different stages. So normal speed up from pipelining that we have already seen in the previous session, that is the average insertion time unpipelined to the average insertion time pipelined. Now what is average insertion time unpipelined, which is equivalent to CPI, cycles per insertion unpipelined, multiplied by clock cycle time of unpipelined, divided by cycles per insertion pipeline. So the below part is pipeline into clock cycle time of the pipeline architecture. It can again be written like CPI unpipelined divided by CPI pipeline, this portion, into clock cycle unpipelined divided by clock cycle pipeline. So we are simply deriving those things just for getting the speed up of from pipelining. Now pipelining can be thought of as decreasing the CPI or the clock cycle time. So in two different situations we are considering pipelining. First situation is we are decreasing the cycles per insertion. So the total cycles required for a particular insertion is being reduced. So we are considering pipelining as decreasing the cycles per insertion, and also we are considering it as reduction in the clock cycle time. Now the ideal CPI, cycles per insertion, on a pipelined processor is almost always 1. That we have already mentioned. The cycles per insertion. So one entire insertion requires only 1 clock cycle. So we are considering 1 as the ideal cycles per insertion. Now pipelined cycles per insertion can be computed as, so CPI pipelined is equivalent to, so cycles per insertion pipelined, which is equivalent to, so we have seen the same thing in our previous example itself, ideal CPI, which is actually 1, plus the pipeline stall clock cycles per insertion. The pipeline stall clock cycle is the cycle number of clock cycle delays that happens due to the stall. Stall happens because of some of the hazards. So 1 plus pipeline stall clock cycles per insertion is the cycles per insertion of a pipelined system. In the previous example you have seen 1 plus 0.2, that is 1.2. So 1 is the ideal CPI time and 0.2 is the delay due to the, so now we can consider it as the delay due to the stall clock cycles, the additional clock cycles because of the stall generation. Now if we ignore the cycle time overhead of pipelining, so we are simply ignoring the cycle time overhead of pipelining, assume that the stages are perfectly balanced, then the cycle time of the two processes can be equal. Then the speed up can be evaluated as CPI, cycles per insertion unpipelined, to 1 plus pipeline stall cycles per insertion. So this is the cycles per insertion unpipelined, and this is the cycles per insertion pipelined. There we consider the stall cycle also. Now all the insertions take the same number of cycles, which must also equal the number of pipeline stages. So number of pipe stages, that actually decides the depth of the pipeline. So in our previous example, the depth of the pipeline is 5, because in 5 stages 5 levels are there for completing the entire pipeline. Okay, so all insertions take the same number of cycles, which must also equal the number of pipeline stages. So number of clock cycles is equivalent to the number of pipe stages. So speed up can also be evaluated as, so the cycles per insertion on unpipelined system can also be given as the pipeline depth, that is the total cycles required for an insertion, to 1 plus pipeline stall cycles per insertion. Alternatively, if you think the pipelining as improving the clock cycle time, the second aspect, that is by improving the clock cycle time, that means clock cycle time improvement means parallelism, that is being implemented by reducing the clock cycle time. The requirement will be reduced. That means improving the clock cycle time means we are reducing the clock cycle time required for the completion of the task. Then we can assume that the cycles per insertion of the unpipelined processor as well as that of the pipeline processor is 1. We are giving an assumption for both unpipelined processor and pipeline processor by using the reduction in the clock cycle time. Both are considered as cycles per instruction. So the number of cycles required per insertion will be given an assumption as 1. So the speed up will be evaluated as CPI. This is the same formula that we have mentioned before. CPI unpipelined to CPI pipelined into clock cycle unpipelined to clock cycle pipeline. It is again equivalent to CPI unpipelined is now 1 divided by 1 plus pipeline stall cycles per insertion, that is CPI for the pipelined system, into clock cycle unpipelined to clock cycle pipelined. So these are the different performance. Sometimes when we need to evaluate the cycles per insertion and the speed up, especially this session is actually intended for finding the speed up when we compare with the unpipelined processor. So every time when we need to go for comparison between two processes, one will be an unpipelined processor and second will be a pipeline processor, and will be given the details of unpipelined, the number of insertions and the cycles and additional things requirement. And similarly for a pipelined architecture, automatically for increasing the parallelism we are doing pipelining, so the number of clock cycle requirements will be reduced. So when we evaluate the speed up, we always get a speed up when compared to the unpipelined system for a pipelined architecture. So we can have a comparison. As we were using benchmark in the previous session, we can evaluate the performance of two processes, one without having pipelining and one with pipelining. Always there will be a speed up due to the pipelining, even after having some stall cycles also. So these formulas actually indicates that even after having these stall cycles, additional delay in time due to some other problems, due to hazards and all, still the speed up will always be better. The speed up will always be better for the case of a pipelined system. So so in the case where the pipe stages are perfectly balanced, the same thing is evaluated again. In cases where the pipe stages are perfectly balanced and there is no overhead, we have already mentioned the same thing before. The clock cycle on the pipeline processor is smaller than the clock cycle of the unpipelined processor by a factor equal to the pipelined depth. Pipeline depth is the total number of stages present in the pipelined architecture. So clock cycle pipelined is equal to clock cycle unpipelined to pipeline depth. Now pipeline depth can be evaluated as clock cycle unpipelined to clock cycle pipelined. Now speed up from pipelining as per the previous formula. This clock cycle unpipelined to clock cycle pipeline will be replaced with the pipeline depth. So the overall speed up from pipelining can be evaluated by using the formula 1 divided by 1 plus pipeline stall cycles per instruction into pipeline depth. So pipeline depth is actually equivalent to clock cycle unpipelined to clock cycle pipelined. It is the stage when we are having all the stages being balanced and without having any overhead on that particular system. So the speed up from pipeline, the same formula is being reproduced with the addition of pipeline depth in place of clock cycle of each unpipelined as well as pipelined architecture. So finally remember this formula: speed up for pipelining 1 divided by 1 plus pipeline stall cycles per insertion into pipeline depth. So simply for evaluation, so if some details are given for two systems, for a processor with pipelining and without pipelining, we can get the details on this, and we can find out the speed up that is being gained because of the pipelining that is added into the new processor. So that's it for now. We will see the remaining, means in the next video we will see in details about each of the individual types of hazards available that I was introducing in this video, that is about structural hazards, data hazards and branch hazards. So that's it for now, and thank you.